Swayam Prabha. Digital India. Educated India.
Okay, so in the last class we discussed about the instability of parallel flows, considering the disturbance quantities are governed by inviscid equation, right, and we derived that equation 10 on the board there. This was derived by defining the velocities, velocity component and the pressure in terms of Fourier Laplace transform, plug them into the disturbance equation that was derived, and that gave us this equation for the amplitude of all these disturbance quantities, right, u bar, v bar, p bar, and from this equations we did eliminate u bar and p bar to get a single equation, right. That's your Rayleigh stability equation. This is quite a famous equation, originally derived by Rayleigh in trying to track the inviscid instability of flows. Okay. Now, at this stage you have to make a conscious decision which way to go. Which way to go? Now, you can see that in this representation, where we define the disturbance quantity in the spectral plane, we have the wave number alpha, we have the circular frequency omega, and what did we decide to do? Well, we said that when we are studying stability problem, unlike the equilibrium flow problem, we must have the liberty to keep them complex. If we keep them complex, then what happens? The alpha being complex means what? I could think of that alpha, the real part will give us a phase, that's what it is, right, e to the power I. So, this will be a phase definition. What happens to the imaginary part of alpha? Imaginary part of the alpha will tell you how the disturbance quantity may additionally decay with x or increase with x, depending on the sign of the imaginary part. What will be the sign? If the sign is positive, so that will be alpha r plus I alpha I, there is a I sitting outside. So, that will give you minus alpha I x. So, if alpha is negative and you are talking about x in the positive direction, then that alpha I would be that correspond to the stable solution, that will damp the solution. But please be aware that a priori you do not know if the flow is going in the positive x direction, the disturbance has to go in the positive x direction. It can go in the opposite direction, negative x, right. If it does so, that same alpha I which I called as stable for downstream propagating disturbance will become unstable for a upstream propagating disturbance. For the time being, I will go with the results that is given in most of the books, except the one that we have written recently. We would only talk about downstream propagating disturbance. When it comes to upstream propagation, we will specifically mention, and you will be aware of it. I will make you aware of that. Okay. So, alpha r is the phase, alpha I determines the stability or instability. For a downstream propagating disturbance, alpha I being negative would be the unstable scenario. Okay. That is about alpha. What about the time variation? Omega also can be a complex quantity. The real part will of course, once again define the phase. The imaginary part, now because of this additional minus sign here, would be that omega imaginary. If it is positive, it is going to be unstable for downstream propagating disturbance. Whereas, If it is negative, then downstream propagating disturbance, that would correspond to stability. Okay. So, having said that, you realize that it's quite difficult to talk about disturbances which are simultaneously varying in space and time. Such problems we will call it as spatiotemporal problem. That means, the space and time would be simultaneously varying for the disturbance quantity, and the corresponding study will be called the spatiotemporal stability or instability theory. And that is somewhat involved. It is not so easy to tackle. Instead, we would take a simpler approach, where we would talk about. So, if this is the all encompassing thing, then we will have sub cases. We can talk about spatial theory. The name itself is suggestive of what? We are going to talk about disturbances that grow or decay in space, right. So, that would correspond to what? So, this corresponds to alpha omega complex. Both are complex for spatiotemporal theory, and for this case what we will find, alpha as complex, okay, while omega will be real. The third possibility is one of temporal theory, and this is what we are talking about here. In temporal theory, what will happen? We are going to talk about disturbances which grow in time. So, alpha will be real and omega will be complex. So, omega by alpha, which we have called as the phase speed, will have a real part and an imaginary part. Okay? And once again, whatever applies for omega will also apply for C in terms of determining stability or instability. That is, if C I is positive, we have instability for downstream propagating disturbance, and if C I is negative for downstream propagating disturbance, it would indicate stability. Okay. So, this is what Rayleigh did. So, considered alpha as real, omega as complex, and written the phase speed in terms of omega by alpha. So, we have a complex phase speed, and we will find out whether it is stable or unstable. You see, these were the days where you did not have computer. So, you do not just simply go and solve it. First and foremost, you do not have analytical expression for U. U is what? Is the equilibrium flow. U is the equilibrium flow that we assumed it to be parallel. That means, it is only a function of y. How do you get it? Imagine, this is Raleigh's time. Prandtl has to come out with his boundary layer theory later, another 40 years downstream. So, U of y was completely unknown, and well, I mean, one could take something, but that kind of assumption would not or approximation would not interest people of Raleigh's caliber. They said, let us figure out if we can get some information about the stability or instability without even solving this equation, and that is what we are going to do next. Okay. So, please pay attention to what we do to equation 11 now. Okay. What Rayleigh did was the following, that multiplied the equation, the stability equation by the complex conjugate of the amplitude of this. So, basically what we have is I have written it down here. So, what we do here, we multiply this equation what is V star? V bar star, this is nothing but the complex conjugate of you realize that all this disturbance amplitude would be in general be complex, right, in general be complex. What does it achieve for you? Well, if it is complex, then you can talk about u, v and p will have their own phase, and they need not be all same. That is why you will have a different values of the relationship between the real and imaginary part, right. So, what we are talking about is then take that equation and multiply by its complex conjugate. So, basically we will just are investigating V bar star multiplied by, I will just simply divide this equation by u minus c. Well, and from now on, just for simplicity, I will introduce prime to indicate derivative, right. So, instead of writing d to v dy square, I will just simply write v bar double prime. So, that is understood. Then I have this alpha square v bar, and then what I have? I have this quantity u double prime. So, that is that u double prime, right, divided by u minus c and multiplied by v bar, and we are going to integrate over all possible range of y that can occur in the problem. So, without loss of generality, we will say the y varies from minus infinity to plus infinity. Now, some of you may be already worried, why am I trying to divide this? What happens if this becomes 0? Then we will be in all kinds of trouble. However, you realize that u is a quantity that is real, is the velocity equilibrium flow, c is complex. So, the real part can match, but still you would be left with the imaginary part. So, the chance of dividing by 0 is precluded when we are studying a temporal stability problem. Although you would have a situation for neutral stability. Neutral stability would correspond to what value of C I would be equal to 0. So, for a neutrally stable flow, you will have a height where this can match. What are we talking about? You see, basically we are talking about the following, that if I plot u versus y, then I could get a profile like this. So, at each height I have a value of u. At some height I could have u of y, I will call that as some critical height, where that should be equal to C of r. So, what happens is basically I will call that as the critical height. So, y C r is the critical height at which u minus C r equal to 0. And if you look at this equation, what happens? This equation becomes degenerate, no? Do not worry about division, but if you look at this equation itself, if I have this coefficient equal to 0, so at that height the order of the equation goes haywire, because that highest derivative is the second derivative, and so you will have a 0 coefficient. So, you can't really talk about. So, it does create a problem, and also you see what happens is if u minus c becomes 0 for the neutrally stable solution at this height, then below this the coefficient is positive, above it is going to be negative. So, across the critical layer the coefficient flips sign. So, we are basically confronted with a situation where we want to get an insight into a solution of an equation which is an ordinary differential equation, no doubt, but it is a variable coefficient ordinary differential equation, and it does not give you immediately a solution, analytical solution. So, that is prompted Raleigh to look at it, but barring that critical layer, specifically for neutral solution, everywhere else there is nothing we are losing by casting this equation in this form. Now, let us look at the terms one by one. So, the first term that I have is this multiplied by this. So, that is basically integral of okay. So, if I do, what do I get? I can do it integration by parts. I can differentiate integrate it once, then I will have right, and this is over the limits evaluated. Then what do I get? Here I will get this differential of this, that will be v bar star prime. Then I have already integrated this once. So, that is there, and then again I am integrating. Now, you can tell me the fate of this term. See, if we are going to the end of the region of interest, that is where disturbances go to 0. If the disturbances go to 0, the conjugate also will go to 0. So, this term does not survive. Okay. And what about this? It is an interesting quantity. This is a quantity times its complex conjugate. So, what do you get? That will be the mod of b prime square. So, this then equal to become minus So, one interesting thing is whatever may be the value of the disturbance, this is essentially a negative quantity, right. All of you would agree with me that this indeed is negative. So, first term gives us this kind of simplification. Term 2, the second term, is rather simple, because that is this minus alpha square b bar star times b bar. Okay. So, I will get minus alpha square So, I will just simply write it as the same way that we have seen this into its conjugate. So, this will give me b bar square dy. That is also a negative sign. So, what is it that we are left with now? We need to really worry about the third term. So, the third term that we have is this u double prime divided by u minus c, and then we have b bar and V bar star divided. Well, we can bring in some kind of simplification by doing this. Multiply the numerator and denominator by the conjugate of u minus c. So, downstairs what will we have? We will have u minus c whole square because we have multiplied by the conjugate of u minus c. Okay. And what about this too? Right. So, now what you get, you can collect all the terms, the first term, the second term and the third term. What do I get? This is negative, this is negative. So, I will take a negative quantity together, and inside I have V bar prime squared plus alpha square, that is that, and this term is this. So, that is also negative, and then we have u double prime times u minus c star divided by u minus c square this equal to 0, right. That is what we want to get. Now, what can you say about the first quantity? Is it real, imaginary, complex? What is the first quantity? It's strictly real, right. So, that is something that we have a clear view. This is purely real. This, of course, this part is real, this part is real, this part is real, but has a complex nature, right. So, I can split it into a real part and imaginary part. The real part will go with this. What happens to the imaginary part of this equation? That is what is written on your this transparency here. 14. The imaginary part is this, right. Because u minus c, the conjugate, is what? U minus c real, that is the real part, and there is a conjugation. So, that will be CR minus ICI, there is a minus I there. So, that makes it plus ICI. Okay. So, now you can understand what you have. You have that equation 14 over there. So, this is where the ingenuity of Rayleigh's analysis comes out glory, that you just simply look at this. The imaginary part of that equation, when it is integrated over the whole domain, yields us this following relation. So, the integral has to vanish. This is a positive quantity, this is a positive quantity, and Ci is something we are looking for. So, Ci cannot be equal to 0. So, we have to make this part equal to 0. How can that happen? That u double prime have to flip sign somewhere. The positive component will negate the negative component, that will yield you a non-trivial solution. So, what it essentially says, that only when this integral is equal to 0, then your Ci need not be 0. Whenever this integral does not yield to a value of 0, then Ci has to be equal to 0, right. So, that is what we are saying, that this integral will vanish when the integrand changes sign in the interval of integration, and this is possible only when the second derivative of u changes sign. Thus, there is a location y equal to y s, I will call that, where the second derivative equal to 0. This point is called the inflection point. You are familiar with the concept of inflection. If I am defining a curved surface, right, y as a function of x, then the first derivative provides us with the slope. A second derivative divided by something gives us an estimate of the curvature, right. So, when the second derivative becomes 0, the curvature is 0. So, if I am talking about a velocity profile, which we sketched before, if I am looking at this, I would have a velocity profile where it will have, let us say, the positive value, then it will have a negative value, I mean 0 value somewhere. Okay. So, there would be a place where I will have u double prime equal to 0. So, this point is called the inflection point. So, what happens is that allowed Rayleigh to draw a very far reaching conclusion, which he enunciated as a theorem, which is called the Rayleigh's inflection point theorem, which states a very simple observation that we have discussed so far, that if I want to get a unstable solution, that means C I non-zero, stable or unstable solution, then what I need? I need that integral to vanish, and that integral to vanish I must have the second derivative to vanish somewhere in the interior of the domain. Please mark my word, I am using the word in the interior of the domain. It is not necessarily at one of the end of the domain. If I try to remind you of boundary layer profiles, you have all heard of Blassius profile, the zero pressure gradient profile. What happens to its second derivative? There the second derivative is 0 right at the wall. So, this Rayleigh's inflection point theorem, which gives us a necessary condition that the second derivative must vanish or there must exist an inflection point, this inflection point has to be in the interior of the domain. It will not be necessarily on one of the end of the domain. Then of course, this theorem does not work, and we gave you an example. A zero pressure gradient boundary layer is a boundary layer for which the second derivative or the inflection point of the velocity profile is right at the wall. I would ask you to show it yourself, just show it. How do we do it? How do we do it? Well, look at the boundary layer equation. Boundary layer equation is a reduced x momentum equation, and there you see the viscous term comes with the second derivative, and on the no slip wall what happens? The second derivative is related to the pressure gradient, streamwise pressure gradient. Now, you see when you have a zero pressure gradient flow, the second derivative is automatically 0. So, we do not have to do anything, we can just enunciate it, and you can realize also that this is a necessary condition. So, if you have a velocity profile and you do not have an inflection point, do not worry about inviscid instability. The good news is whenever you have a velocity profile with inflection point, you would find that there would be some frequencies for which the flow is going to be unstable. Basically, inviscid instability gives you a much more of a critical scenario, unlike what we would expect from viscous analysis, right. So, this is what was done by Rayleigh, and as I told you that he did it without the equation. All he did say that if I can measure the velocity profile, or I can get an analytic expression by looking at the velocity profile, the equilibrium condition itself, I can say whether that scenario depicts a stable or an unstable condition. Okay. However, little later, sometime later, Feuertoft came into picture, and he said, look, in enunciating that inflection point theorem, what we have done, we just simply looked at the imaginary part of that reduced equation. What happens to the real part? What happens to the real part? That is what Feuertoft investigated, and he came out with an improved version of Rayleigh's theorem, which now goes as by the name of Feuertoft's theorem, and which says that a necessary condition for instability is that u double prime times u minus u s is less than 0 somewhere in the flow field. What is u s? U s is the velocity value at which the second derivative is 0. So, basically it is the velocity value at the inflection point. See, at the inflection point the second derivative is 0, but velocity is non-zero, of course. That is what we are calling as u s. How is this condition obtained? Well, we can do a little investigation and find out how Feuertoft's condition comes about. Now, if I call this equation as A, let us say, the Rayleigh's theorem investigated the imaginary part of A. Let us look at real part of A. What do we get? Well, we get the following, that the equilibrium flow information that comes in from this right. This is related to the disturbance quantity by putting all the disturbance quantity on the right hand side, and that we have seen already what this is going to be. Okay. So, this was and the corresponding imaginary part, we keep it handy because we require that also. That is the following: C I times u double prime divided by u minus c whole square, and then we had square dy. Let us call this equation as B, let me call this equation as C, capital C. Okay. So, we have this. Now, I will do a little bit of manipulation, nothing great. We will multiply B by CR minus US divided by CI, and the resulting expression will add it to equation C. Okay. What we get is the following. See, whenever I multiply this quantity, so whatever will happen to C will happen only on the left hand side, nothing will happen on the right hand side. So, the right hand side remains the same. On the left hand side, what we get is the common part, that will be u double prime divided by u minus c square, and then what happens? You see, I have multiplied this equation by this. So, what will happen? This C I will cancel, and I will have C R minus U S. So, I add that. So, what do I get here? C R will cancel out, and I am going to get this equation u minus U S, okay, and times v bar square dy equal to minus of, well, we have this expression, it is this, and of course, this is less than equal to 0. Now, you can clearly see what Feuertoft's theorem is giving us. Feuertoft's theorem saying that this quantity has to be negative, right. The imaginary part was strictly equal to 0, but here what we are saying that this quantity has to be negative, and if this quantity has to be negative, then what happens? This part, the integrand has to be somewhere negative, otherwise it will not give us the thing, because this is a positive quantity, this is a positive quantity, and that is exactly what he is saying here. Feuertoft is telling us that you must have u double prime into u minus U S should be less than 0 somewhere in the flow field. Okay. So, basically, since this condition given by Feuertoft includes both the real and imaginary part of the original Rayleigh's equation, it is considered to be more general, stronger condition, right. So, basically you should remember both of this theorem together, and you can see that condition of instability, if you write like this also includes Rayleigh's inflection point theorem also, right. Rayleigh's inflection point theorem is also a subset of it, because that equation has been used in arriving at this. Okay. So, that is what is known as the inflection point theorem of Rayleigh and its improvement by Feuertoft. However, we must keep this thing in mind, that both these theorems provide necessary condition, but they are not sufficient, because who guarantees that after doing that integral you will indeed get a 0 contribution. It is not understood immediately. That is why please do understand, this is a necessary condition, but not a condition. Okay. Okay. So, having exhausted the discussion on inviscid instability, let us focus our attention on viscous instability of parallel flows. Tell you what, that idea given by Rayleigh, supported by Kelvin and other luminaries of that time, always doubted this, that whether there was at all any need to study viscous instability. We have talked about it in the introductory lecture. We said that was a major turning point. There was a debate, a paradigm shift, whether we need to stay with inviscid instability or we need to do viscous instability studies. Viscous instability studies equations first written down by Orr in Ireland and Sommerfeld in Germany. The corresponding equation is called the Orr-Sommerfeld equation, which is different from your Rayleigh's equation. Rayleigh's equation talks about inviscid instability. Corresponding viscous instability governing equation is called the Orr-Sommerfeld equation, and that is what we are going to discuss now. What we are doing, once again, we are looking at linear stability. That means the perturbation fields are smaller, so that in deriving the disturbance equation, we would make small perturbation assumption, omit the nonlinear terms. However, we retain the same equilibrium flow description. The mean flow or the equilibrium flow is once again given by a parallel profile, right. That is, u is a function of y only, and it is in the streamwise direction. Since we have already talked about it, you know this is a parallel flow. You are saying that all points at different x's at the same y has the same value of u. So, that means the streamlines are parallel. That is why it is called parallel flow approximation. However, we note that despite making such simplifying assumption, viscous stability theory is able to predict many things in detail, like the effect of pressure gradient, effect of mass transfer in terms of blowing and suction. They are predicted quite well by viscous stability theory. Now, we know in hindsight that this is indeed a valuable addition, but it had its moment of uncertainty in those days when it was propounded for quite some time till it was verified theoretically experimentally. Okay. We would also talk about heat transfer effects. I would depart from what most of the books write. They say that it captures effectively. I disagree with that based on some of the work that we have been doing in recent times. One of our students just defended his thesis, where we see that the moment we add heat transfer, all the stability theory, linear stability theory has some insurmountable difficulties depending on the flow configuration. For some cases, it does show good effects. You can use linear stability theory, but in another major subclass you cannot do that. So, we'll come to that at a later stage, but let us now go ahead and rederive those equations depicting the stability or instability of the parallel flow. Now, we have noted by now that in instability analysis, we start off with identifying an equilibrium flow. So, in this case, let us say that we have a mean flow, which is quite generic of what Prandtl did. Prandtl came out with the boundary layer analysis and boundary layer flows, and if we consider such steady boundary layer flows, we want to study its instability. So, the mean flow is obtained from boundary layer flow. Boundary layer flow is a kind of a simplified version of the Navier-Stokes equation, but when it comes to obtaining the governing equation for the disturbance quantities, please mark it. It is important that we do not make any assumption about the disturbance quantities. They are still given by Navier-Stokes equation, and what you are seeing here written down are given in a Cartesian frame. Okay. And this is what I have written down the Navier-Stokes equation for the total quantity. So, u is the total component, the v is the total component, w is the total component of the velocity profile. Okay. That now will split it up into an equilibrium flow and a disturbance quantity. So, those three momentum equations ought to be supplemented by mass conservation equation written like this, and next we define any flow quantities which I have used it as lowercase q would have a mean flow or the equilibrium flow which is steady. Okay. So, this capital Q which defines the equilibrium flow is a function of space only, not time, whereas all time dependence come into the disturbance quantities. And since we are doing a linear theory, we put in a small parameter epsilon to assist us in collating terms. Okay. Now, in addition, we say that we go by the same parallel flow approximation, right. So, now we have focused our attention on 3-dimensional flows. So, the mean flow will have also 3 component, capital U, capital V and capital W, and the moment I say we are looking at parallel flow, we immediately realize capital V has to be equal to 0. Capital V non-zero does not allow you to make parallel flow approximation, right. Whereas, U and W component once again have to be only a function of y to keep the stream sheet. Now, please understand streamline is a concept of 2-dimensional flows, but that again depends on our point of view. If I go along the flow, along the direction of the flow, I can once again define the flow as 2-dimensional. So, again I can consider the streamline along the flow direction and view it as a vector, and that is what is called as the vector potential, right. Most of you have done the computing course, you know that vector potential is a generalization of stream function in 3 dimension. Okay. Do not worry about it, we will not get in there until unless we come to genuine 3-dimensional flows. At this point in time, let us just simply appreciate that for parallel flow approximation to hold, we will make u as a function of y, capital W as a function of y. Such an assumption is called the parallel flow approximation or quasi parallel flow approximation. Because what happens when we have a boundary layer, it is quite sacrilegious to talk about no growth. We all know boundary layer grows, right. But if the growth is negligible, I can still study the flow locally and say, look, if I am studying at this station, I take the velocity profile, the dependence on x is weak. So, let us omit that path. So, basically what we are saying that in the argument list, we should have a y comma x, but the x dependence is much weaker, it is a stronger function on y. Okay. That is what is called as a quasi parallel approximation. Okay. So, what do we get? Well, we do get those disturbance equations, and we have done it for inviscid analysis, and I would let you to look at these equations and decide for yourself if they are correct or not. Well, this term directly comes from del u del t, because the mean flow is not time dependent. So, all the time dependence would come from the disturbance quantity. What about this term? This term comes from u del u del x. Now, u has capital U plus u prime. Okay. So, I will get this capital U times this. This is order epsilon term. This is order epsilon term. Okay. What is omitted? The term that is omitted is basically u prime into del u prime del x, that is epsilon square. So, that term has been thrown away, because we are studying linear stability theory. There is also a mean flow term, right. The mean flow term is what? Capital U times del u del x, but del u del x is 0. Okay. Capital U does not depend on x. So, we just have this term. Same thing we have W into del u del z. So, W will have a order 1 quantity, and this is your order epsilon quantity. So, this comes in order epsilon equation. What about other term? What about other term? We will have V del u del y, okay? And that contribution only would come from the mean flow part, which I am writing here by an ordinary derivative. So, that is what you get. The pressure gradient term, I have written it like this, and you realize that this equation is written in non-dimensional form. That is why I have gotten the Reynolds number coming here, right. So, what you do is basically you assume some kind of a length scale and some kind of a velocity scale and write down the Navier-Stokes equation in those things. So, say let us say for length scale, if you have x, y, z, you refer it to some length scale L, and the velocity components whatever we have, the total quantity, we will talk about this. What about time then? Time will refer it to a time scale. Time scale will be brought out by L by u infinity, right. Use that to non-dimensionalize the equation, and then of course, the R e that we have written there, we will get it as u infinity L by nu, the kinematic viscosity, right. And that is why you see that from P will be non-dimensionalized with respect to what? Rho times u infinity square. We are focusing our attention on incompressible flow. So, rho is a constant. So, I will non-dimensionalize the pressure by rho infinity square. That is what we are getting here, that del p del x, rho has disappeared, and you get in front of the diffusion term 1 over R e. The same way y momentum equation can be simplified to yield this differential equation for V prime, okay, and the corresponding equation that is written for the z momentum equation written in the bottom. Okay. Okay, so these are 3 equations. This has to be supplemented with the perturbation equation obtained from equation of continuity. That is fairly straightforward. You can directly write it down. Next, we discuss what is called as a normal mode analysis. This is something that people have been doing now for nearly 100 years, and what it basically does is tries to study one mode at a time. Okay. So, what happens is the disturbance quantities, you are going to write it like this. So, what we are writing, the disturbance quantities that we are writing here is in terms of its all possible harmonic components written in terms of the Fourier Laplace transform. So, these are those disturbance quantities. We are writing them down in terms of their amplitude. So, u prime has amplitude, which I am calling it as f of I, right. V prime I am just writing it as phi of I amplitude. W prime, let us say we have used the expression h of I, and p prime I will let us say call it as pi of y. So, this is the pure y dependence of the equation. In addition, we will have to write all its phase. Now, phase term, once again we will first write it down and then we will justify what we have written. We are looking at 3 dimensional disturbance field. So, y dependence is here. So, I have x dependence written here. I will also have to write down the z dependence, right, and the time dependence of course comes out like this. And now, what you will have to do? Ideally speaking, if we are looking at the generic case, then we should have written it like this, that this equals to all possible values of alpha and beta. And what we are doing now? What about omega? If I also would have written down an integral over omega, that would correspond to spatiotemporal analysis, and I mentioned to you that is quite tough. Like in the Rayleigh's equation, we just simply looked at the temporal analysis. Here we will do something different. We will instead look at, let us say, the spatial analysis by fixing a real frequency omega naught. Okay. We will do that, and then what we are going to do here, we are going to talk about alpha and beta as complex. That will be your spatial theory, right. So, we are looking at spatial theory, which corresponds to omega naught equal to constant and alpha beta as complex. Okay. So, I think we will stop here, we will begin from here the next class, and we will see where it leads us to.